Today we are going to see operating system unit 8 deadlock. We are going to see about system model, deadlock characterization, methods for handling deadlocks, deadlock prevention, deadlock avoidance, deadlock detection, recovery from deadlock, combined approach to deadlock handling. What is a deadlock? A set of blocked process, each holding a resource and waiting to acquire a resource held by another process in the set. Example, a system has two tape drives, P1 and P2 each hold one tape drive and each needs another one. So P1 is holding a tape drive and P2 is holding a tape drive. P1 needs the tape drive of P2 and P2 needs the tape drive of P1. Then only each process can complete its execution. So no process is going to complete the execution in this context since each one is waiting for other process to get completed. So this type of situation is called as a deadlock. Example, semaphores A and B initialize to 1. For the process P0, wait of A. So now P0 is waiting for the A to be gets completed. So the process P1 at the same time waiting for the B to complete. The A is held by process P1 and B is held by process P0. So both the process is now in waiting state. P0 needs B to get completed A and P1 needs A to get completed B. So both the process cannot be completed at this point of time. An example, a live example, we can take the bridge crossing. Traffic only in one direction. Each section of a bridge can be viewed as a resource. If a deadlock occurs, it can be resolved if one car backs up. Several cars may have to be backed up if a deadlock occurs. Sometimes starvation is possible. Starvation is nothing but waiting for a long time. System model. Resource types R1, R2, Rm, CPU cycles, memory space, and IO devices. These are all called as resources. Each resource type Ri has Wi instances. Each process utilizes a resource as follows. A request will be sent to the process for a resource to get utilized and it will use the resource and after that it will release the resource. Deadlock characterization. What are all the characteristics happens when deadlock is going to arrive? Mutual exclusion. Only one process at a time can use a resource. So only after that process gets completed, the other process can use its resources. Hold and wait. A process holding at least one resource is waiting to acquire additional resources held by other process. So in this situation also, deadlock arrives. No preemption. A resource can be released only voluntarily by the process holding it after the process has completed its tasks. And circular wait. There exists a set P0 to P0, P1 and goes on after Pn. Again, P0 is waiting. A waiting process such that P0 is waiting for a resource that is held by P1. P1 is waiting for a resource that is held by P2. And Pn minus 1 is waiting for a resource that is held by Pn. And P0 is waiting for a resource that is held by P0. So at this time, each process will wait for the resource held by the next process As this is a circular type, so none of the process is going to get completed, then it's a deadlock situation. Resource allocation graph. How will you allocate the resources to the process can be depicted as a graph. What is a graph? A set of vertices V and a set of edges E. V is partitioned into two types. One is process P1 to Pn and R is the resource R1 to Rn. What is the request edge? That is the directed edge. P1 is a process request resource Rj. What is assignment edge? Is the directed edge of resource Rj is being assigned to process Pi. So the resource allocation graph contains all these symbols. For the process, a circle, resource type with 4 instances. Instances are nothing but the copies of the resource is depicted by a square, and Pi request instance of Rj. So is depicted as a circle that is process requests the resource Rj. Pi is holding an instance of Rj. So assignment edge will be allocated for from the resource Rj to Pi. The arrow marks Pi when the Pi is holding an instance of Rj should be from Pi to Rj, and Pi request instance of Rj means Pi from Pi for resource Rj. The edges are drawn. Example of a resource allocation graph. We have 3 processes. In this graph, P1 is requesting resource R1 and P2 is assigned with resource R1. So 2 types of edges, assignment edge and a request edge. Another type, claim edge, can also be created. We will see it later. So P1 is a process which requests resource R1, which is held by P2. So P2 can get completed only when it gets R1, when it requests R2, an instance of R2, which is given to P2. Then process P2 gets executed and it will release the resource R1. But R2 is held by P1, so the P1 cannot be completed until it receives a resource of an instance of resource R1, which is held by P2. So P2 is also requesting R3. So P2 needs R1 is held by P2 and R2 is held by P2. It requests the resource R3. But R3 is held by P3. So now P3 does not request anything. So therefore P3 with its resource R3, it will complete its execution and release the resource R3. It will be given to resource P2. So P2 will have all the resources R1, R2 and R3 and finishes its execution and releases R1. So P1 needs R1. So P1 gets R1 and R2. With this resources, it will finish the execution. There won't be any deadlocks here for all the 3 processes. But sometimes a deadlock happens like this. Now the P3 is also requesting a resource R2, which is held by P1. So P1 needs R1, which is held by P2, and P2 needs R3, which is held by P3, but P3 needs R2, which is held by P1. It's like a circular weight. So therefore, this process will not get completed. Let's suppose a resource allocation graph shows a cycle, a complete cycle. There won't be sometimes that you won't get a deadlock. That means any resource allocation graph with the cycle won't have any deadlocks. So we will see this with an example. Sometimes it will also get deadlock even if it has a cycle. That is also we are going to see with an example. Here the process P1 requests resource R1 and it holds the request, it holds the resource of R2. P3 requires the resource R2 and which is held by both P1 and P4. But P4 doesn't want any request. So it is going to complete its execution and release the resource in R2. Now R2 is requested by P3, so the P3 will complete its execution with R2 instance, and the resource requested by P2 is completed. So therefore, a resource is given to P2, therefore P2 will get completed. So both the resource R1 instance requested by P1 also gets released. At the same time, R2 instance also get released by P4. So therefore, P1 gets all both the resources R1 and R2 and completes its execution. You have a cycle between P1, R1, P3, and R2. So even though the cycle is there, in this example, deadlock doesn't happen. The basic fact is, if graph contains no cycles, there won't be a deadlock. If graph contains a cycle and only one instance per resource type means, then deadlock occurs. If several instances per resource type means possibility of deadlock, but may not be possibility of deadlock will also be there if you have a several instances per resource type. If only one instance per resource type is there, so if more than one process requires the same resource type of the same instance, then definitely there occurs a deadlock. Methods for handling deadlocks. Ensure that the system will never enter a deadlock state. Allow the system to enter a deadlock state and then recover it, or ignore the problem and pretend that deadlocks never occur in the system, and you continue your process. What is deadlock prevention? Restrain the ways requests can be made. Mutual exclusion, not required for shareable resources, must hold for non-shareable resources only. So non-shareable resources may get deadlocked because of this mutual exclusion. Hold and wait. Hold and wait must guarantee that whenever a process requests a resource, it should not hold any other resources. The required process to request and be allocated all its resources before it begins execution, or allow process to request resources only when the process has none. So this will reduce the hold and wait concept. So the deadlock can be prevented. When resources very low, also starvation is possible. No preemption type. When no preemption happens, deadlock happens, but it can be avoided. It can be prevented if a process that is holding some resources requests another resource that cannot be immediately allocated to it, then all the resources currently being held are released. If process P1 requests resource R1 and it has R2 and R3 resource, if that process P1 does not get the R1 resource, means it has to release all the R2 and R3 resource also. Preempted resources are added to the list of resources for which the process is waiting. So therefore, this R2 and R3 can be used by some other process to get completed. Process will be restarted only when it regains its older resources as well as the new ones that it is requesting. The process P1 can be completed only when it gets all the resources of R2 and R3 which is released by P1, and also the new request which has been made by the process. So deadlock can be prevented. Circular wait. Impose a total ordering of all resource types and require that each process request resources in an increasing order of enumeration. So every process should get all the resources and then it has to start the execution so that the process need not wait for the resources for the next process. So therefore, circular wait can be made prevented. And what is deadlock avoidance? Requires that the system has some additional priori information available. Simplest and most useful model requires that each process declare the maximum number of resources of each type that it may need. The deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there can never be a circular wait condition. Resource allocation state is defined by the number of available and allocated resources and the maximum demands of the process. So a resource allocation state is based on the available and allocated resources for the process and also the demands by the process. safe state. So when a process requires any resource, system must decide if immediate allocation leaves the system in a safe state. So what is a safe state? The process should not enter into any deadlock state. So that state is called as a safe state. That is possible only if there exists a safe sequence of all the process. So sequence P1, P2 up to Pn is safe only when each Pi resources that Pi can still request can be satisfied by the currently available resource plus resources held by all the Pj with j less than I, which means P1 will not enter into the deadlock state. That is, it will be in a safe state only when the P1 resources whatever it asks and also whatever it holds, which is satisfied by the P1 to get completed execution. Then after it gets completed its execution, it will release all the resources which it has, which can be used by other process, the next process for its execution. If this is not possible, then Pi should wait until all the Pj has finished. So the P1 needs to wait until all the Pn gets finished. When Pj is finished, Pi can apply needed resources, execute, return allocated resources, and terminate. When Pi terminates, Pi plus 1 can apply all its needed resources and so on. So therefore, there won't be any possibility of deadlock in the circular wake. So the safe state can be ensured like this. What is the basic factors? If a system is in safe state, no deadlocks will be there. If a system is in unsafe state, there will be a possibility of deadlock. How will you avoid it? Ensure that a system will never enter an unsafe state. The sequence of process when you are using, you have to ensure that the sequence of process also, none of the process in the sequence gets deadlock, by ensuring the safe state of all the process in the sequence. So this is the diagrammatic representation of safe, unsafe, deadlock state. So when it is in a deadlock state, this process is in unsafe state. When it is in safe state, means there won't be any deadlock. Resource allocation graph algorithm. So a graph is maintained for the resource allocation. You have claimage Pi to Rj, indicated that process Pi, Pj may request resource Rj represented by a dashed line. Claimage can be represented in the graph algorithm with a dashed line. So this dashed line represents that particular process may request the resource at the future. So claimage converts to request H when a process requests a resource. It can be converted as a request H, that is the dotted line, dashed line can be converted into a normal line only when the requisition happens. When a resource is released by a process, assignment HT converts to a claimage. Resources must be claimed a priori in the system. So all the process should request the resources whatever it needed before it starts the execution. Resource allocation graph for deadlock avoidance. So P1 is holding the resource R1 and P2 is requesting the R1. This will not enter into the deadlock stage when this process P1, P2 is in safe state. So will you identify that as with the diagrammatic representation with the claimage. So resource R2 is another resource available for the two process. But if P1 requests R2 means R2 will be allocated to P1 and P1 has the R1 resource. So with that resource, P1 gets completed its execution and release all the two resources which is requested by the P2. So the claimage represents that in future, the P1 may request R2 resource and also P2 may request R2 resource. Unsafe state in resource allocation graph. So now R2 is held by P2 and P1 is waiting for R2, and in this diagram, P2 is requesting R1 and R1 is held by P1. So therefore, P1, only when P1 releases R1, P2 can it's completed its execution because it is having already R2 resource. But the P2 is requesting R1, which is held by P1. So if suppose P1 claims R2, P1 will not finish its execution as the R2 resource is held by P2. So which needs the R1 resource which is held by P1. So this state is called as an unsafe state, and this may get a deadlock. Banker's algorithm. So multiple instances when it is used for each resources, Banker's algorithm can be applied to identify the safe state and unsafe state. Each process must prior claim maximum usage of resources it needs. When a process requests a resource, it may have to wait for some time to get its resources. When a process gets all its resources, it must return them in a finite amount of time after completing its execution. Holding the resources by the process definitely will may reach the deadlock. Data structures for the Banker's algorithm. Let n equal to number of process and m is the number of resource types. What is available is, if available of j equal to k, which means k instances of resource type Rj is available. Maximum n cross m matrix. If max of I, j equal to k means, then process Pi may request at most k instances of resource type Rj. Allocation n cross m matrix, which means if allocation of I, j is equal to k, then Pi is currently allocated k instances of resource Rj. Need n into m matrix. If need I, j is equal to k, then Pi may need k more instances of Rj to complete its task. Need of I, j is nothing but maximum of I, j minus allocation of I, j. Now, need is 10 resources means, take for an example, maximum resources it needs is 50. Allocation is only 5. So what is the need is maximum minus allocation. So what is maximum? 50. But allocated is only 5. So what is the necessary resources needed for the process is now 10. The safety algorithm. Let work and finish be vectors of length m and n respectively. Work equal to available. Finish of I equal to false. Initialize the variable finish of I equal to false for all n process. Find an I such that both finish of I equal to false and need should be less than work. Work is the availability. So therefore, the need should be less than availability. So for example, totally I have only 50 resources, but the process requires 100 resources means the need is 100 resource. That means it is 100 is not less than or equal to the available resource 50. So therefore, you cannot get executed that particular process. So if both the condition satisfies, then work will be allocated with the resources it needs. With that, the job gets finished and it continues for the next process there until it reaches the end process, whichever gets computed or whichever gets to be executed. Suppose if none of these two conditions in step 2 is satisfied, then it will go to step 4. So now finish of I will be equal to true for all I, then the system is in a safe state. If suppose it comes to the step 4 with the request of 100 resources, but we have only 50 resources, then it is a failure one. So therefore finish of I cannot be true. If now one of the process in the sequence finish of I not equal to true, that is if it is false, definitely the system will not be in a safe state. So you cannot allow those process to enter into the system for execution. Resource request algorithm for process Pi. Request equal to request vector for process Pi. If request of j equal to k means then process Pi wants k instances of resource type Rj. If request is less than need, go to step 2. Otherwise, raise error condition since process has exceeded its maximum claim. The request by the process is 100, but definitely it needs only 50. That means it's an error. So it is claiming the more number of resources by the process. If request is less than available, so request is the less than the available value. So available is 150 and the request is only 10 has been made, then it can go for step 3. Otherwise, it needs to wait until the resource gets available. Pretend to allocate the requested resources to PI by modifying the state as follows. Available equal to available minus request. Allocation equal to allocation plus request. Need equal to need minus request. So what is available is the available minus request. So it has requested 10. Availability is 50. So 50 minus 10. Now it is available only 40 resources. Allocating the resource which is requested, that is already 0 allocation has been made, but now it has allocated the requested for 10. So if it is allocated, what is the allocation now? 0 plus 10. 10 is allocated for the resource I, for the process I. So what is the remaining need? Need of the process to get complete its execution. Need minus request. So what is request is 10, but it needs 50 for its complete its execution. Then what is the need value? Already 10 allocated. Now 50 minus 10, 40 is needed by the process to get complete its execution. If safe, the resources are allocated to PI. If it is unsafe, PI must wait under old resource allocation status restored. This should be checked for each and every process requisition for the resource. Example of Banker's algorithm. So 5 process, P0 to P4, 3 resource types, A, B, C. A is 10 instances, B is 5 instances, and C has 7 instances. When you take process P0, allocation is 0, 1, 0, but the maximum needed by the ABC is 753. What is available now? Allocation minus maximum. So the resource for A is 10 instances. A has 10 instances, but the maximum request made by the P0 is for A is 7 only. So what is available? 10 minus 7. If it is allocated to A of process P0, then the availability of A is only 3. And similarly, 5 instances of B, it requests P0 requests 5 instances of B. So the allocation is 1. Maximum 5 instances, the allocation is 1. So 5 minus 1, 4 will be the available B value. But the instances of B is 5. So 5 minus allocated 1 is going to be 5 minus allocated 5, and the remaining is going to be 1. So the availability is 5 minus 1, 4, 4 minus 5 instances. Out of that 5 instances, 4 is allocated, so therefore 3 will be the available. And similarly for C. So 7 instances, maximum is 3 only. It has now, but the allocation cannot be done now because the availability is already allocated 3. So 7 minus 3 is 4. So 4 is already allocated to other process. So therefore the availability is only 2, so which cannot be allocated for the P0. The availability is 2, but it is asking for 3, it cannot be allocated. The availability of B is 3, but the maximum you have 5. So you can allocate 1 instance. The content of the matrix need is defined to be maximum allocation. The system is in a safe state since the sequence P1, P3, P4, P2, P0 satisfies the safety criteria. If everything is allocated and every process gets completed one by one, then it is in a safe state. Example P1 request 1, 0, 2. That is, it is less than 3, 3, 2. So the request for ABC is 102 only, but the availability is 3 comma 3 comma 2, then it's a safe state. Definitely we can allocate and the process gets completed. So executing safety algorithm shows that sequence P1, P3 to P0 satisfies the safety requirement. The deadlock detection. So how will you identify the deadlock? Allow system to enter a deadlock state. You use an algorithm to detect the deadlock and recover the process from the deadlock. Single instance of each resource type. Maintain wait for graph nodes or process. PI if PI requests PJ, if PI is waiting for PJ, then periodically you have to invoke the algorithm whether PI has entered into any cycle. An algorithm to detect a cycle in a graph requires an order of n squared operations where n is the number of vertices in the graph. Resource allocation graph and wait for graph. In this resource allocation graph, each process will be allocated with the resources, and some process will request other resources to be allocated. So with this resource allocation graph, we can draw a corresponding wait for graph, which is for the if you take P1, P1 is requesting R1 and it has R2. So therefore, P1 needed R1, which is held by P2. So therefore, there will be a connection between P1 and P2. So P1 is requesting something from P2. That is the given in the corresponding wait for graph. And P4 requires something from P1. So when you see from P4 to P1, there will be an arrow, which means P4 is waiting for P1 to release something. So likewise, you can draw for P2, P3, and P5. Several instances of a resource type. Available, a vector of length m indicates the number of available resources of each type. What is allocation? An n cross m matrix defines the number of resources of each type currently allocated to each process. What is a request? An n cross n matrix indicates the current request of each process. If request ij equal to k, that process pi is requesting k more instances of resource type rj. Detection algorithm. Let work and finish be vectors of length m and n respectively. Initialize work equal to available. For I equal to 1 to n, if allocation not equal to 0, then finish of I equal to false. Otherwise, finish of I equal to true. So allocation is not equal to 0. So some allocation is being made, then finish of I is now false. That is, it has not completed its execution. Otherwise, finish of I equal to true. If there is no allocation, finish of I equal to true. So we have to find an index I in such a way finish of I false, and also the request should be less than the available work that is available. So request is 10 and the availability is 50. So if this is less than, so therefore no such I exists. So therefore we can go to step 4. The step 4 is nothing but everything is completed. So therefore finish of I is false now. For some I between 1 and n, then the system is in deadlock state. Moreover, if finish of I equal to false, then Pi is a deadlocked 1. So when you see in step 2, finish of I equal to false and request is also less than work, if both the conditions satisfies only, then it will continue for 3. If there is no, finish of I is all, everything is true, which also means everything is completed. If request is greater than the work means which cannot be allocated, so therefore definitely a deadlock will occur. So we have detected a deadlock, so we won't allow that particular process to enter into the CPU for execution. So if all the conditions satisfies, the allocation will be made and the finish will become true. So again, step 2, the next process, the sequence will be taken, again checked, and if it is in safe state, we are going to allow it to get executed. So example of detection algorithm in the same way, P0 to P4, 3 resource types has been used ABC, each resource of several instances. So when you calculate the P0, P2, P3, P1, P4 way, it will result in finish of I equal to true for all I. Everything will be finished. So detection algorithm usage. When and how often to invoke the detection algorithm? So how often a deadlock is likely occur? We need to identify that, then we can invoke the detection algorithm accordingly. How many processes will need to be rolled back? That should also be identified by the CPU. If detection algorithm is invoked arbitrarily, there may be many cycles in the resource graph, and so we would not be able to tell which of the many deadlock process caused the deadlock. Recovery from deadlock process termination. About all deadlocked process, about one process at a time until the deadlock cycle is eliminated. In which order we have to choose the process to get aborted. So priority of the process, if it is a lower priority, we can abort it. So how long process is computed and how much longer to completion? If it takes more longer time, then we can abort it. Resources the process has used, which is needed for more number of process, means we can abort it. Resources process needs to complete. The requisition of the resources is more, which is held by so many process, then we can abort this process. How many process will need to be terminated? So we have to identify how many number of process needs to be terminated in order to recover from the deadlock. Is process interactive or batch process? If it is a batch process, only one process of the batch cannot be terminated. So the complete batch process needs to be terminated. If it is an interactive process, that one particular process can be terminated. So we have to identify whether the process or interactive or batch. So recovery from deadlock can also be made through resource preemption, selecting a victim, that is minimizing the cost. Rollback, return to some safe state, restart the process for that state. Starvation, same process may always be picked as a victim, include number of rollback in cost factor. Thank you, students.